Alright, so the first question here is asking us to find the mean number of weta per square meter. So they haven't given us the mean, but they've given us a graph. On the next page, you see over here, they'll give us a table that we're to work out the mean from. And so to find the mean of something, we can do it by hand, or we can use our graphics calculator to enter in all this data that they've given us to calculate the mean for it. So what we can do for that is we can use our graphics calculator and go into the stat menu here and enter in all the information that we know. So firstly, we need to enter in all of the values. So we're going from 0 through to 7. Cool, so we've got all the different values for that data set entered in now. Our next step is we need to find the value for each of these. Now, you're not going to get it perfect. It's a bit of it is reading off a graph, so there's going to be a slight possible reading error, or like what you interpret in, but it should roughly give you about the same value, which we'll talk about shortly. So having a look at this first one, you should have to see that it's slightly above the 0.05 line, so I'm going to enter that in as 0.06. This one 0.17, 0.275 for that one, 0.24 for that one. So it's just me reading off. You might get very slightly different values, but overall, when we calculate it in the end, it should still come out the same number. So now we need to go into calculate. Now make sure it's set up right. So make sure that says list 1, and the next one, the frequency of that list is list 2. And then from there, let's go back. And so then we're going to calculate for one variable, and you'll see that the mean at this kind of 2.5758 mark here. Now that's the mean for this, but in terms of the next question here where it says use your tables in an appropriate value for lambda, so what it's talking about is these tables here at the back of your book, these ones here. Now what you'll see the values for lambda is they only go down to 1 decimal place, so we're just going to round our value to 1 decimal place as well. So we're going to round it to be the lambda for this one to be 2.6. So having entered the mean and we've chosen an appropriate lambda value, what we're going to do is then complete this question here. It says to find the theoretical probabilities for each x on the graph. So we've got our lambda now, which is 2.6. So if we go into our distributions, into our Poisson distribution, and since we're only calculating for one number at a time, we're going to use the PPD, so the point distribution. Make sure it's on variable. And so for 0, so when lambda is 2.6, we're going to calculate that for this first value here. And that will come out to be 0.074, so it's just going to be a little bit higher. Kind of up there, kind of see that on the graph. Then we're going to do the same for the next value. And so on through the rest. Cool, then for part C, use this value of lambda from B, so the 2.6, to find the theoretical probability that there are 2 or 3 weta in one square. So what we need to do is find the probability when x is equal to 2 and the probability of when x is equal to 3, since it's combining two individual values, and then we're going to add them together. So we've already done that. We found that the probability of 2 is 0.2510, just 4 decimal places, and then the probability for 3 is 2176, so 4 decimal places. Then we combine that probability to get the probability of being 2 or 3. do that by adding them together. So that comes out with a probability of 0.4686. Then for D, the probability that there are no wetters in two separate areas. So you need to find the probability for each of them, which will be the same. And since they're two separate events, we're going to times the two probabilities together. So we're going to go probability that there are no wetters, which is 0.07427. And so for the probability, that's just going to be this value squared, because two separate events, which comes out with this really small number here. So that's times 10 to the power of -3. So if I was to write that as a value, it'd be like this. The way that I kind of remember it is kind of if it's a -3, it just kind of tells you how many zeros come in front. So like 1, 2, 3. All right, for this next one, so an area of 2 square meters. Previously in the question we've been talking about per square meter up here. So what happens with the lambda value? Instead of being just lambda, it becomes like 2 lambda, which is just 2.6 doubled, which is 5.2. So the lambda for this question that we're going to be using is 5.2, and we want to calculate the probability that there were no more than 4, so up to and including 4. So we go back into our distributions again for the Poisson. Now this time we're using multiple values because we want 0, 1, 2, 3, 4. So we're going to use the Poisson cumulative distribution, so PCD, and we want everything up to and including 4. So we're going to put x as our 4, and our lambda is going to be 5.2. And there you go, there is our probability. All right, so this question is asking whether or not the Poisson distribution is good for the situation of simulating these wetters. So firstly, Poisson, we use it for rare events. It must be positive. It's an event of something that's discrete, so like counting wetters over a continuous interval or space. So we're talking about square meters, which is a continuous thing that is measured. All right, and then the assumptions for the Poisson is that they occur at a constant rate, which we kind of can presume we're going to make the assumption that they do. The events are independent of each other, so the number of wetters that are found aren't dependent on the other square meter of wetters on this cable, which may or may not hold up because maybe wetters are congregated in a certain place because of, I don't know, food source or something like that, and they can't occur simultaneously. Yeah, so it's unlikely to find two wetters directly occupying exactly the same space. So that is unlikely. So that one holds up. If we were to look back at the distribution of that, back up the top of the page, what you can see is that this distribution follows pretty closely. They're both right skewed. They both have unimodal, so they'll both have one mode, and they kind of follow. So overall, I'd say that this is a pretty good fit using the Poisson distribution to model the situation. Further evidence that you can use is looking at the Poisson table at the back here, and if we were to look for 2.6, which is here, you can see that the values go from 0 all the way down to 11, whereas our distribution only goes from 0 to 7. Now the chances of that is because since the probabilities from 8 through to 11 are really, really small, it's possible we just didn't see any wetters there, hence why the distribution is so small. But in reality, it's potential that, yeah, there could be those smaller probabilities, but yeah, from this graph it doesn't completely match up either. But yeah, overall it's a pretty good fit. Then for this next page, it's pretty similar. You're going to enter in all the data again. So all of this data here is going to be entered into the calculator to calculate the mean. One thing to watch out for in this question is when it talks about finding the standard deviation down here. I'm pretty sure the answer is wrong for this particular one, so don't worry if your standard deviation doesn't quite match up.